Please tell me where to begin.
You can.
Okay. Okay. All right. Good morning, everyone. We will be meeting today, and so we're meeting today. We'll also meet tomorrow, similar time. Take a look at radio pulsars. So one of the most fascinating objects in the universe. Not just because I work on them, but quite a bit. So the name itself was coined by a reporter, apparently. Find lots of gadgets that are named by this label pulsar, terrestrial objects, right? Watch, and I think there's also car, and so on. So you will find that pulsars actually is all in one gadget. The ones that I just mentioned. It involves rotation, dynamo energy storage, energy conversion, space motion, acceleration, braking, sparking, revolving. It has its emission, radiation, and also keeps time. We have been looking at these objects for more than 50 years now, and essential information comes to us as a function of time. Density is a function of time. Everything else is all free a function of time. And everything else that we have learned about it is inferred based on such observations. Of course, the story began famously with Jocelyn Bell, who was a graduate student at Cambridge Radio Telescope, and she was planning to study twinkling of stars, twinkling of objects which are not really stars, very distant compact objects, extragalactic objects, which would twinkle due to the irregularities in the or homogenities in the medium that spans within the solar system, which is the interplanetary. And that's when she saw these periodic blips, which of course have the intensity going downward. So these are decreases in intensity. In intervals, people would have easily dismissed this as some interference from some terrestrial source. And she already pursued this to the level that people had to take it seriously and established not only one, but about 4 such signals. And that she established that they are indeed real. And so, as I said, she was studying interplanetary scintillations, and in the process, because this twinkling, which is the density variations, fluctuations on short time scales. To be able to study those, you need ability to take pictures at short intervals. That meant that the response time of the whatever recording of the instrument had to be turned down. And that was normally not done because people used to actually stare at the sky. As you know, longer exposures give you better sensitivity and so on. But in the process of doing this, one was somehow opening a completely unexplored parameter space. And of course, surprises were waiting to be revealing themselves, and they did. So this is one of the lessons that we should remember whenever we are trading into a completely unexplored parameter space, or opening the parameter space, which is not explored earlier, can have rewards. So of course, initial excitement was, understandable. Said after they dismissed the signals, are they from spacecraft or are they from some civilization, and that was the exciting thing actually. So of course, this was the first evidence of strictly periodic pulses. The chart record that saw, and but as more and more pulsars were discovered, it became clear that one is looking at a new class of astronomical objects, which of course turned out to be highly magnetized neutron stars. After about 6 months of secrecy, finally the announcement came in early 1968, and eventually her supervisor was awarded prize, not according to the controversies associated with that. But what is fascinating about what followed as a set of arguments is actually very interesting. You will find that each one of these arguments that I'm going to go through are individually very simple arguments. Okay, you will agree to them as sort of readily acceptable. But when put together, they form a pretty powerful, set of selection criteria that turns out that only few projects will qualify. So the first one, of course, was natural. That whether the signals were coming at the same time, day after day. What time is the sky time, not the solar time. Okay. Now you know that we spent extra 4 minutes to look at the sun again in the same way that we looked at the previous day, because we have moved, right, by a degree or so in our orbit around the sun. So you will find there is this 4-minute difference per day, which can be used profitably. Another way of looking at it is you're doing a simple parallax measure. You're standing at one place today, looking at the direction. So you're standing at another place, which is almost about 0.3% of the circumference of the orbit. And then object, again, to see if this is in the same direction. And if it happens to be in the same direction, what do you conclude? The object must be very far. Right? If it's near, then you would find that the direction has changed a little bit. So that argument proved that the source must be well outside the solar system. These are like 20 questions that we might be playing, right? Each question has answered yes or no, and then together we find we have excluded a huge number of possibilities. Right? Then a small pulse width. The pulse width was about the blip occurred for maybe tens of milliseconds. That immediately is used often in astronomy as a light travel time argument, saying the source were to be bigger than certain size, or source were to be of certain size. The intensity variations will have to have a time scale which is corresponding to, the length. So that if you assume the size, then divide by c, and you will get a time scale. Okay. If you have the pulse width that you see, then you can estimate the source size. Okay, base source size you can have. So immediately the shortness of the pulse width told you that the source must be smaller than certain physical scale. There were pulsating stars known earlier, Cepheid variables, as you might have heard in different contexts, where the oscillations are there, physical oscillations, where the period is proportional to 1 upon square root of the density. Now, already one had found a range of periods for these objects. And if you translate that, it would amount to square of that range in the density. It's very difficult to imagine a single class of objects having such a wide range of densities. So they were ruled out itself. And then one had, by the time to look at how the period changes. And the period changed very, very slowly. Okay? The period was practically constant, but did show measurable change, which that even if you compare the energy that was received as the only lost energy, right? And translate that back to percentage of the energy lost, right? Because we know the rate at which it's slowing down. You could estimate the total energy it might have. That came out to be large. And now you have, so that means a massive compact object, big inertia involved. And that later led to the conclusion that it must be a compact star like a white dwarf or neutron star. Certainly not the extraterrestrial civilization same signals. So, of course, one had already begun to hear about possible ways this light can be produced, and the basic lighthouse model was put forward by Tommy Gold and Franco Puccini, and where you have, one rotation into one pulse. Of course, between the two possibilities, neutron star and white dwarfs lost out very quickly once some faster rotating pulsars were discovered. And there you can simply understand the argument as, centrifugally, it's not possible for a white dwarf to rotate at that speed. It will simply destroy itself. Yes. You can do that simple sum that you do for normal classical mechanics. And then, what was nice about the cracked pulsar is that its association with the supernova explosion in 1054 AD, which Chinese had recorded meticulously, and the age of pulsar that one could estimate. We will see how it is estimated. Yes. Age of the cracked pulsar matched roughly with the age of the nebula that one saw around it. And the energy purchase also well. And the real evidence for where exactly this radiation is coming from which object, how it's produced, location within the object was clarified by the famous observation of the Veda pulsar, who proposed the magnetic pole model. So, which meant that they interpreted the patterns that they saw in polarization as due to the free structure that you see within the cone in which this radiation is produced. So, of course, Devarati must have taken you through all this story of compact stars and so on. So, I'm not going to repeat that. So, run through that very quickly. But it is important to mention that Bade and Zwicky had predicted neutron stars. In fact, soon after neutrons were discovered, and as an end product of supernova explosions, and of course, one saw this as an example beautifully. Thankfully, Prague explosion was recorded, and one could see this association. And what follows, we will focus on rotation powered pulsars. Means energetics is driven by sheer rotational kinetic. Okay. We will not dwell on the cousins, which are where the magnetic fields play an important role, or energy source, or accretion plays an important role, I think. So these are simple rotation power pulsars. I will skip this. This you must have heard a lot about, right? This also you must have been, because I think she must have talked about how to probe the interior, right? So I will skip that, except as popularly known, described 1 teaspoon of this matter, which is so dense, the equivalent of mass of humanity. So that's how dense it is. It's basically nuclear density. So when one saw these objects and inferred things like, of course, the speed of rotation or the speed was immediately known. This is discovery time itself, but it can follow through and measure its slowdown. You could also estimate the strength of the magnet. Now, both these being extremely high, comparison with the normal stars had, people had an easy way of understanding it by simply invoking essential principles that we are all familiar with: conservation of flux, right, and conservation of angular momentum, both relating to the different aspects. So, why high magnetic fields? If you say sun has, let's say, 100 Gauss feet, million kilometer size, right? You hammer it down to 10 kilometer radius. You have reduced the radius by 10 to the 5. Square of that, right, is sort of bigger reduction in the area, right, 10 to the 10. So you can easily see flux conservation will give you of the order of 10 to the 12 Gauss at the surface. Similarly, the cores of the stars which are going to collapse and produce this compact object might be rotating at some speed. And now we are again going to speed that up by exactly similar factor. There, you're doing the moment of inertia. And so everything was fine. We were generally happy. Till they realized that it's not easy. When they try to look at cores of stars or try to estimate the speeds which cores of stars rotate, they found that it's not really rotating as fast as required to, even after factor of 10 to the 10 increase, right? For it to produce the kind of speeds. By then, later, of course, pulsars were also seen to be zipping through the space at speeds which were of the order of typically 100 kilometers per second. So both these were puzzles, right? First difficulty was how to explain the speeds of rotation. And the other one was why they're moving so fast to give them that velocity, right? So what is nice about this picture that came up quite independently by researchers, sets of researchers, is that when the supernova explosion occurs, there is a neutrino flux that comes out, carrying most of the energy associated with this explosion. And if there is any asymmetry, lack of spherical symmetry, then you will find that there will be a recoil, right? Reaction. That if it's asymmetric, will amount to a kick to the central object. And that kick, if it's centered, going through the center, the net result of the kick, then of course there will be a space motion, right? But if it's off-center, much the way, I don't know how many of you play football, if you kick the ball little off the center, you will find not only it will move the direction of the kick, but it will also spin. And this is what they proposed as an explanation, combined explanation for both, which is beautiful. Except now you can see that when you kick a ball and it, side little off centered, and when it moves, the spin axis is always perpendicular to the direction of motion. Now, this is a good prediction to test. People actually tested that. Okay, to see whether the motions are in the direction perpendicular to the orientation, the rotation. So, of course, all these things are done with all that we see is in projection. So remember, we don't have access to the third dimension, but we at least can check this in projection. It's true, and indeed, it has been found to be true for young pulsars. Some of the old pulsars seem to forget what their original kick was, and quite possible that they have lived long enough that they have changed the course of their motion, right? Or something else has happened to them. Rotation axis. Of course, the details of the duration of the kick and variety of other detail issues are still not fully understood, but it's beautiful that this very simple prediction can be tested, and this particular case may not be also true. So that explanation relieves the difficulty, the most difficulty that I had about explaining why pulsars are rotating as fast as we see them, while the cores before they collapse were not rotating as fast. So they get the spin the time of the birth, almost safe, right? Of course, the motion that I mentioned, space motion, it's then compare that speed with the speed of sound in the medium through which it's flowing through, and you will find it's way higher than that, right? And so what will happen? You produce a wake, right? And that will shock the material. You see actually the signs of it. If you look around Pulsar, you will see a beautiful nebula. In this particular case, I don't know how well this is seen. This is called Beta Nebula shape that it describes. Very nice and symmetric, right? Particularly, delineation is much better here, although the contrast is. Okay. Let's come back to the key aspect. Pulsar itself, the basic lighthouse model, as I said, was proposed very quickly, but it had to wait for the polarization observations on the Vela pulsar from Parkes to really illustrate where exactly the radiation is coming from. As I said, this famous observation showed that indeed it is coming from the magnetic pole around the planet. How do we know that? One saw the position angle. What is the position angle of polarization? This is of linear polarization, of course. Is the plane of oscillation of the electric field, right? Of the electromagnetic radiation. And that you can imagine as it propagates, it's also looking at a certain plane. That plane has certain orientation with respect to whatever reference you might take vertical or horizontal. That was seen to be rotating as you went through the pulse. Okay? It was very nicely interpreted as due to our looking through a small section at a time of the cone, right? And so either the observer can be seen relatively crossing and sampling the chord like this, okay, or the beam can be, observer can be stationary and the beam can be swept past that. Essentially, you basically get information across this chord. Now you can ask across this chord, if I begin from here, where I begin to see some intensity, what is the orientation of the field line? It is going to change as I go through it. And this is exactly the traverse that was seen. Okay? Which meant you're seeing the orientation of the magnetic field lines in projection. Okay? If you take the cone of the dipole field and look down on the poles, you will see that the field lines will be seen to be radially coming out. Right? And those sampled at some distance away from the center would look like this. If you sample it right through it, of course, it will be one orientation, go to the other orientation. Right? So this certainly provided a way of, where did I go? So the exact shape, of course, depends on how this cone is inclined with respect to the rotation axis and how far you are from it. You can imagine that if you are very far off, you will see a very slow change, right? This won't be as steep. This will be a very gradual change, right? When you are right at the center, you will see a sudden change, right? A step change and so on. So on and so forth. So you could actually use this backwards to even estimate important parameters of how this magnetic field axis is oriented with respect to the rotation axis. The information that you can get sitting here, right? And also how far you are away from magnetic axis. Okay, but the essential picture for this to be interpreted that way, the requirement is that the electric field direction is defined by the magnetic field line, and for which the picture that is put forward and agreed upon largely is that given the high magnetic field strength, the charged particle tries to move around. It will be constrained to move along the field. Any transverse momentum that is not aligned with the direction of the local magnetic field will be radiated away instantly. One way of imagining this, I will come back to this later, is you are familiar with gyration of charged particles around the magnetic field, right? Imagine the gyration radius to be zero, and that it is, or it gyrates for a very tiny fraction of a time and loses energy in that mode. And of course, it's free to move along the field. So you will find the charged particles, when they constrained to move along the control field line, when it beats on the string, you will see the field oscillation also confined to the plane of the field. So this is called curvature radiation, which is very similar to the synchronous radiation. And so, of course, since the speeds at which these particles are moving, it's also beamed narrowly towards along the tangent, the field. If it were not so, if they were radiating very broad angular sector, each one of them, then at any given time, you see radiation from here, radiation from there, which would have different polarization in print. And when you add different polarization states together, you will find you are depolarizing. right? So the high degree of linear polarization that was seen was important to conclude various things, including the fact that we are looking at very deep radiation. That means that would tell you about the speeds of this object, speeds of the charged particles, Lorentz factors, if you mind. What was clear that once you were seeing certain intensity and it came from an object which is that small, you can find out how much was radiated, right? If something was radiated by a certain size object, you can ask if it were to be a black body, what kind of a temperature it should have to produce so much output at a given frequency. Of course, it's a frequency dependent question. It turns out that you will get extremely high temperatures implied. These are not physical temperatures. These are equivalent black body temperatures, okay, that you would have to hope to explain the observed intensity, which might be produced by a completely different process. Okay? But what it meant is that you have no incoherent process would produce such a high brightness temperature. So you need to invoke high degree of coherence. This is what we must have found when, when large number of particles radiate in phase, you will see that the radiation fields will add. When they add together, you will find the intensity goes as square of the number of contributors instead of incoherent addition of intensities, which is just number of contributors times the intensity. And that is the gain that one will be looking for. So remember that we are looking at extremely coherent radiation. Pulsars. It's like masers or lasers. Okay, it's equivalent to that in terms of coherence. This is what I was saying about the curvature radiation. This is just a bit of it. So of course the curvature radiation depends on the curvature of the path that the particle takes, where you can think of it as equivalent acceleration, which is making it go around this path, and you can use even simple formulation. Of course, you do the special relativity to get the appropriate time scales. Okay. So an observer here will see a tiny blip of a narrow blip of light along this curved path because it's radiating in such a narrow pole. If it changes its direction of motion, you will miss to see the light. Okay. So given all that put together, it turns out this is the typically Lorentz factors of about 10. Okay. Radius of curvature of the order of 7 centimeters. You will get radiation at 0.7 megahertz. Okay. And you can scale from there. Find out. Of course, you will find that as you increase the Lorentz factor, you will get higher and higher frequency radiation. You can see that as you increase the speeds, the Lorentz factors increase, you are going to spend very little time, okay, in the line of sight to the observer. And shorter the time scale, broader the spectrum, right, and richer intensity as well because of the boosting. Okay. So the emerging picture has been that we're looking at fast rotating highly magnetized neutron stars with a well-defined rotation axis and an arbitrarily inclined magnetic axis. Okay. Magnetic field, this axis is so arbitrarily oriented. And the radiation comes from cones around aligned with the magnetic axis. So of course, these parameters are, ever changing. this is the sort of rough range. Magnetic fields, now, magnetars, if we include, have to go to 10 to 15 Gauss or something. But even as low as 10 to the 8 Gauss fields have been seen in some of the pulsars. The shortest period, of course, is little less than 1.5, but around that, and that's that's close to the fastest rotation that the neutron star can. Okay. It's at the limit of it's allowed to rotate at. And of course, this has increased. Now there is a almost 11-minute pulsar seen, pulsar-like object seen from one of the telescopes in Australia recently. So these numbers will get revised, but the basic picture remains. Now, if you really look at it, it's a matter of principle, you'll find a rotating dipole is actually radiating magnetic dipole radiation. It's electromagnetic radiation at the frequency of the spin of the object. So if something is rotating at 1 second period, the radiation is at 1 hertz. That is nowhere close to the radiation that we see. We talk about megahertz, gigahertz, and so on, right? Radio. But the real major radiation is actually happening at that low frequency. Now, what happens to this radiation? This radiation tries to go outward, but it encounters medium which doesn't allow it to propagate. Because you can see that there will be some plasma, there will be some, if you're familiar with the term plasma frequency, right? Or basically the interaction between the medium and the radiation will decide whether to be allowed to propagate or not. And here the situation is the frequency of the radiation is so low compared to the typical frequency of few kilohertz at the plasma frequency of the interstellar medium is. Although it's a very what should I say, the density of electrons is very, very small there. Even then, it's high enough for stopping this radiation. So what it does, when something is stopped, it will try to push and the material will get collected, right? And then the ramp pressure of that will resist further expansion and some equilibrium size should be reached. So this will create a cavity around pulsars. Pulsars will create a space around them by pushing things around them away till they can push it. Okay? And pulsars sit in beautiful cavities that they themselves make. Of course, as I said, what reaches us in radio is at very, very high frequency, right? And that is typically frequencies around or below 1 gigahertz. And given its steep non-thermal spectrum, which means higher intensity at lower frequency, they are seen very brightly at low frequencies. Again, similar thing is there even in our ionosphere. Ionosphere stops propagation, okay, below about 10 megahertz or so. Okay, typically. We don't see the radiation. But by then, the radiation from pulsar is so weak that it's not going to do anything. Interesting. But locally, it can create a cavity of significance. So how do pulsars, what do they do in their life? Okay, born in the fashion that we described, supernova explosion, the end product of it, and then they're losing energy, they're radiating energy, right? And the major energy loss is what I described as this low frequency radiation. The other frequency radiation loss associated with it is tiny in comparison. Okay, what we see in radio is not the main machinery, is the noise it makes, right? So, pulsar, of course, loss of energy causes pulsar too, because it comes at the expense of its rotation. Kinetic energy, it slows down. And the magnetic dipole radiation also weakens, right? And then there is something else happens which we will see. The dynamo weakens. What is this dynamo related to? Which you must have used on your bicycles also in the older days to light a small bulb, right? Where there is a small gadget that rubs against the tire, right? And you have a magnet inside which is rotated, and an EMF produced by that is used for lighting the small incandescent bulb. I'm not talking about the LED lights. But even the LED lights, it's a good example because it becomes relevant as we go. So there you know that as you pedal faster, the light will grow brighter, so slow down. So the same thing happens here. See how it affects. And when the dynamo becomes weaker, the light does not grow more, right? When you slow down. This causes death radio pulsar. We'll see how. The main things governing it are, of course, this is the energy loss, which is direct, uh, you know, expression that you can get simply by taking the rotational kinetic energy and differentiate it with time, right? And you will get I omega dot if half I omega square, right? Was the But then if you say that this energy loss is due to the dipole radiation, magnetic dipole radiation, then one knows how to estimate that, right? Loss due to the radiation associated with or described by the dipole radiation or the magnetic dipole radiation, where the magnetic field strength is involved and some parameters of the star. And then when you plug that in, it allows you to estimate the surface magnetic field. And people have been doing that. This is how we know that pulsar magnetic fields are of the order of 10 to the 5. You can also do by knowing that the present period is this and it began with a very short period, and this is the present rate of slowdown, and the rate of slowdown also changes as a function of time. You can put all that together, that will only make a factor of 2 difference. But even if you take the present period and say this is the rate of change, how long it has taken to come here, you can estimate the sort of characteristic age, and which is what gives you a fair idea of how long the object has been around. Now, while the pulsar slows down, does it slow down when the period increases monotonically? Ideally, largely yes, but the answer was found to be no pretty soon after the pulsar's discovery. The Radhakrishnan in Manchester found a big change, a significant change in the rotation rate of the Vela pulsar. And that was of the order of 1 part in a million or so, okay, a few parts in a million. And that's a very significant change because you change your watch by that fractional amount, you will find soon it will begin to lose noticeable amount of time because of this accumulating, right? And so that's what happens. The slope changes a little bit. You find the rotation rate changes. The difference in the time that it should have kept and the difference in the time is presently showing, okay, becomes very significant, and that can be. So pulses seem to arrive earlier than expected, which meant that it is rotating a little faster than it was earlier, which means yes, suddenly spun up. Okay, and this has been understood as due to start quakes of sort or rearrangement of the quantum inertia. And again, conservation of momentum will give you that change. Again, there are more details associated with that, tied up with areas of neutron stars, the way it behaves and it recovers from such a glitch. And it's been an area of intense investigation for many people. The important question is it possible to predict when the next glitch will occur? And people have tried their hands at it, and there seems to have been a fair amount of success in certain cases, where within a week's time one can actually predict in certain cases for certain pulsars when the glitch will occur. Okay, because of the processes that lead to glitch occurrence, which is the built-up stress. So it's like the way it works is it's like a bucket to empty itself after it's filled to the brim, right? So depending on how much you empty it at the time, take this action of following the it's reaching to the brim. That will decide when the next time the similar situation, right? And this simple analogy seems to work in the sense of picking up stresses. So there's some critical stress at which things give up. In terms of overall evaluation, you will see that the initial periods, although they were very small, they lengthened to by many a few orders of magnitude as they go on. And the other question is, over time, do the magnetic fields undergo any change? And the answer is no for isolated pulsars. Magnetic fields, at least during their lifetime, which is typically of the order of a few million years to maybe even a few tens of million years, the magnetic fields don't seem to be there. So this is a diagram which we'll look at again. This is the magnetic field versus period, and this is where the major pulsar population sits. Typically around 10 to the 11 to 13 Gauss, and periods ranging from the present time. Most of the population that we see is around this 0.1 to, let's say, a few seconds, 0.1 seconds to a few seconds. In this diagram, the pulsars can be seen to be born at this end with whatever magnetic field they begin with, and then the rate of change of period is very high initially, and this being a log scale also, they will zip through this region very quickly in a very short time, and then they will, appear to slowly moving across this, because now the change in the period is actually quite large, again on the log scale. So you will find that they pile up here. That's where most of them are seen. There is something called a death line here, which we'll elaborate on. There is no, rarely any object is seen beyond this. Okay? And this is that line which I was mentioning, that dynamo becomes very weak. Okay? We'll see what fraction of the dynamo, what aspect of the dynamo becomes weak and how it is supported. So again, looking at this picture, how am I doing with the time? Okay, so let me spend a few minutes. So pulsar begins its life very short periods with whatever magnetic field it gained at the birth, moves horizontally in this diagram that I showed you, which essentially means that it does not change its magnetic field, moves horizontally, and as the period lengthens, it reaches a period beyond which the dynamo has become too weak to do something interesting that produces the radio radiation. So it's dead as a radio pulsar after that. Okay. Now it can keep on losing energy through magnetic dipole radiation. Correct? And as it does, it will keep on slowing down. And over long time scales, if there are processes that take over, which reduce the magnetic field, which it does, as there are models which describe actually how the magnetic field can decay, forced by the slowing down of the, or affected by the slowing down of the pulsar eventually, on time scales which are very, very long. So it might just stay there, what we can call a graveyard, right? And do nothing. That in terms of giving us any light. But if it has somebody who takes or has a companion who sees this condition and is prepared to help, then by prepared to help, you'll see quickly what I mean. Prepared to help in terms of bringing back the dynamo action alive, which means it has to be spun up, right? It has to be made to rotate faster. If that is possible, and if the companion is willing to help, or when it's able to help, you will find the pulsar, the neutron star, which is dead radio pulsar, can be brought back to life. It's done beautifully in binary systems where there is an explicit companion, and based on when the companion is ready to help, donate matter which carries the angular momentum, the orbital angular momentum, and deposit it on this compact object. Of course, leading to processes, the accretion, disk formation, so on, right? And the stuff that gives you X radiation that people must have described already. So X-ray binaries, phases, okay, are the phases in which the dead pulsar can be brought back to life. It's recycling at the extreme. Imagine 1.4 solar masses has been recycled, right? And so you will find that based on what has happened to the star before it was ready to help, okay, what has happened to the neutron star before the companion was ready to help, will decide where it can be brought in. Okay, if the companion happened to be a high mass star, which evolved quickly, relatively speaking, and was ready to donate matter, okay, that mission could begin early, it can bring back the dead radio pulsar back into action, pretty much without having had dropped the magnetic field strength. Where it will bring it depends on how fast it can accrete and all that. And that is this line, what is called the spin-up line. There is some limit for the rate at which the matter can be accreted, okay, given the strength of the magnetic field. Okay? And so that will decide the sort of equilibrium. Period line is called, and so it will be brought back. But if it's an intermediate star, which might take long time to evolve, okay, and come to the stage of flow and accretion, then you will find by then the magnetic field might have decayed for this compact star. And so when it comes back, it come back with this reduced magnetic field and to be seen somewhere. Another extreme case of that is low mass. And these are low mass X-ray binaries which are completely observed and studied. you will find that they will bring this pulsar back to spin up line, which actually you will see the periods implied here are extremely small. They can be spun up to millisecond periods. Now, however, the rate of energy loss because of although they are rotating as fast as when they were born initially, magnetic field strength is so low that they do not radiate as much energy. Okay, the rate of energy loss is so small, orders of magnitude small, that they live forever. In the sense that for them to cross the deadline, the time required is enormous, of the order of 10 to 10 years. Right? So they are going to be, once they are brought back, they will be there all the time. Similar period object born at high magnetic field would have finished his life within about 10 minutes. Okay? So this is the story of so most pulsars, you can see, you can ask how many pulsars would have this luck of being helped come back to life. Turns out that most large fraction of overwhelming fraction of pulsars are actually born in binaries. And depending on their companion and of course the survival of the binary, remember there are going to be explosions, right? At the time of the explosion, there's going to be a situation where depending on the masses and energy, we find the binary can disrupt, right? The mass loss and so on. So the life history will differ. Of course, one had these pictures of how these kind of evolutions take place. You have primary and secondary. Then you have, depending on slight mass difference, you can see how you can, if the binary survives, of course, you can go through this motion where you produce a low mass system based on the initial mass of the secondary, right? You can also produce double neutron stars based on, of course, this will involve two explosions. Binary is to survive really behind the so on and so forth. I will not go through these details, but I will mention that there's 1974 saw the discovery of binary pulsar, where so the relativistic binary with both of them, neutron stars going around each other, orbital period of about 8 hours, and the motions amounted to high speeds like a second. And this allowed one to actually check one of the predictions, GR, in terms of seeing the change in the orbit of the pulsar. The other one is a neutron star. Okay? Probably a pulsar which may not be pointing towards us. And so you will find that instead of the period strong remaining, the orientation constant as a function of time, it changed over time, a fashion that was predicted by the GR. And this amounted to indirect detection of Deshpande waves. Okay? The energy loss that affected the orbital motion and it evolved over time in a tiny way, but it could be measured thanks to the accuracy to which you can time the pulsars. That means you can measure the arrival times of the pulsars expected and observed, and the difference gives you a lot of information about the rotational history of the pulsar, okay, and the location of it. So this, I'll stop here for today. Now there is even a better lab for testing other effects, or even several well-known effects to a finer level. System which is this famous double pulsar, where both the objects are visible as radio pulsars. And so now you have less ambiguity about the orientation of the orbit and so on, which you could resolve earlier. Except that at the present time, it has gone in hiding, the second pulsar, because of certain precision effects, again tied up with the GR. Okay? It is not looking towards us. People are waiting for it to come back to our view. Then the precision, okay, which will be additional information that we need. I'll stop here. Any questions?
Have we really observed pulsar dying and then reset?
We don't. We don't live long enough to see follow a particular pulsar to go through that entire cycle. But we can see that population as a whole, okay, then we cannot follow any one individual's by track. We look at population and ask. So, like we can estimate the typical death age, right? We don't live beyond this. We can estimate by looking at the present population, the distribution of it. And this is, we see this demarcation, the combination of period and magnetic field, that there are no objects on this side of it which have detected population. And that is tied up with, tomorrow we'll see how that really affects, how that is understood as the lack of data knowledge. Right? Just imagine, that's where the analogy with daily light would come, where there is some minimum voltage required for light, right? It's sort of a simple and bulb, right? So if you pedal fast enough, of course the LED is glowing. Then you will find there is a critical speed at which, below which you will not produce enough EMF, which is the minimum required for, even there is certain minimum required for the LED to light. And so you'll find if it's whatever, 0.3 volts, 0.6 volts. If the EMF produced is below that, the light will suddenly stop going. Exactly similar situation occurs. It's tied up with the coherence. Okay? What is required for coherence and how the conditions for coherence cease to be produced after the potential difference falls below.
Sir, is there any other natural bodies is also available who emit signals like pulsars? Any stable signals? Just
there's nothing as stable as pulsars that we know of. Even, I mean, the level of stability that the pulsar signals provided as a function of time or stability of rotation, given of course that the fact that they are slowing down, can measure the slowdown rate and make a prediction of when the next pulse is expected. It's like the clock is. It's not that it's keeping time exactly, but even if it's changing, you know the rate at which it's changing, so you can predict. So given that, it can actually, the stability compares well with even the atomic clocks. So they are as good clocks as, or sometimes better than the clocks we have as atomic clocks, which are actually pretty accurate clocks. But there are no other objects that we know of. Because remember, it started with the level of inertia, right? Finally, the initial argument itself, why we concluded that objects with high mass, right? Massive objects must be born, right? And producing such a stable periods.
So why does the rotation axis of pulsar?
Why does the rotation axis of pulsars precess? Apart from as an isolated object, of course, in the case of binary and so on, there are these other effects tied up with the misorientation of its axis with respect to the orbital axis. So on. But in general, as an isolated object, like the top precesses, right? When the rotation axis does not match one of the symmetry axes, okay, you will see precession. Wobbling is natural. That's a free precision. So
the yellow line indicated here as a strong magnetic field, right?
Which ones? Oh, you mean here in this picture? Oh, the bands. Yeah, those are basically the cones.
The magnetic field.
Yes, aligned to the magnetic axis.
When it goes backwards and strong magnetic field cause jets and we don't have why?
There is, yeah. So here, of course, there is a particle flow. We have particle flow along the magnetic axis. In fact, they are the ones who, as we described, they are the ones which produce the radiation levels. Absolutely. The charged particles streaming along the lines, okay, within this cone, and giving out the light that we see, as well as the streaming particle flow also does something interesting in the surrounding. Both of these you visit research. But these are not, there the jets are along the rotation axis. Okay. Distinguish that from. So these are not like macro quasars.
How could we test GR if the objects come in our view?
If the object?
If the objects come in our view, the double pulsar, how could we test GR? We can like study their orbit.
Yeah. You study the orbit and the evolution. Okay. That's what we do. And it's like, the light is made available at certain orientation on that sphere, which is the pulsar. Its wobble and so on is also going to change the intensity, right? In a certain fashion. You know whether it has changed the orientation from the polarization characteristics, because you can find out everything about, the relative orientations of the magnetic axis with respect to the rotation axis, how far the observer is from the rotation axis, the magnetic axis, and the rotation axis, of course. And if any changes occur there, precision and so on, all these effects can be tracked down, right? And can measure over time. Eventually, these are the systems that are going to coalesce and produce the gravitational waves. Right? They're already producing gravitational waves. We are not seeing the gravitational waves directly, but the manifestation of that energy loss in terms of modification of the orbit.
Sir, I want to ask a question. Like the rotating lighthouse model is same for the double pulsar. Rotating lighthouse model.
Yeah. It just happened to be both of them are looking towards us, and both of them are alive yet. Okay. It could happen that one of them is a dead it has crossed it, gone into the graveyard, right? It's possible, and only one of them is active and pointing towards us. Remember that we have about we can see typically about 20% of the pulsars, given their cone of size of the cone in which they radiate, and they could be arbitrarily oriented, right? Firstly, the cone itself would be arbitrarily oriented with respect to the rotation axis, and the entire system might be arbitrarily oriented with respect to our line of sight. One can estimate that by simple calculation. That you expect to see only about 20% of the objects which are, even if they are all active. Among them, it could be that one of the pulsars in this, even the Hulse-Taylor binary, where one of them is a radio pulsar, the other one is a neutron star. We do not know whether it's active radio pulsar because it may not be pointing towards us, right? Now, at the present time, if you look at this double pulsar itself, you would mistake it for a pulsar where it's not a double pulsar, right?
So I asked this double pulsar.
Yeah. So right now, we are in a state, if we happen to have observed it only today first time, you would see the other pulsar doesn't exist, this is only single pulsar, right? Although we can estimate the mass of the other star by doing the timing measurements, and we might infer that it's also a neutron star. That much inference we can do, but we still don't see radiation, and it might suddenly emerge, right, after some time during its precession cycle. It might begin to look at this. Yeah.
Why should the flux be the planet collapses? The field.
Yeah, because there's nothing happening to the magnet per se, na?
But it's like when the supernova happens, it's losing energy.
It's losing energy, which is so it's losing this potential energy, right? It's losing the potential energy. That has got nothing to do with the magnetic field. It's not extracting energy from the magnetic field, right? Even this, radiation that we see, right? It's not extracting energy. There are magnetic field, magnetically forward objects like magnetars, where it does. In fact, some of the asymmetries might be imprinted by the presence of matter. Yeah.
The pulsars can also be seen by like does that body.
Yeah, the typical temperatures pulsars in the same group is probably about 1,000,000 degrees or something like that, right? So they can be seen in X-rays. They have to be very near, tiny objects, right? They don't have huge amount of flux in the X-rays, but some of them have been seen. The nearest of the objects have been seen as plasma. These are isolated objects, of course. Then they are in action as binaries, X-ray binaries, and so on. Of course, there are, the other radiation which dominates. Another question? I should check with the stop sharing. Chat. Should check. does the rotation of pulsar affect the polarization radiation? Yes, I mean the polarization position angle itself changes. I'm just reading the question. Is that visible? Yeah. So the rotation does not affect the polarization, but the polarization seems to be changing as a function of the phase of the rotation cycle. Does that answer, Sumit, your question? There are, of course, effects which affect the polarization state that we will see, which are more special realistic effects rather than like aberration and so on, right? You will see the apparent polarization be different than the original polarization of the radiation left because you're seeing it from a different frame. So there will be effects to that effect, but not intrinsically. Any other question? Okay, I'll probably stop. This must be already late for you. I hope the next speaker is not. All right, thank you. See you tomorrow. All right, I'm leaving the Zoom. Is that okay, Prakash?
Yes, Desh. Although you don't have to log out.
Pardon?
You don't have to log out.
Oh, I see. I will just stop.
Yeah. The next speaker will use it.
Oh,
yes.
okay.
Yeah.
Right. So sharing I have stopped, right?
Yes, that's enough.
We'll just minimize this.
Sure.
So, I will leave this thing here. I don't have to speak tomorrow. Okay, thank you. Just in case the next person. Yeah, of course. Remind me. Right. Should have said.
close to